Bon, alors, je suis ravi de pouvoir donner ce cours et je suis très heureux d'avoir été invité par Jean-Philippe. Alors, je vais maintenant faire le switching vers l'anglais. Donc, I'm going to talk about behavioral macroeconomics and is it a new paradigm? By way of introduction, let me say a few things about mainstream macroeconomic models. As you know, these models, very interesting and very influential, have a number of hypotheses that are questionable. They assume agents that are maximizing their utilities in an intertemporal framework. That seems to be fine. But then using all available information, including the structure of the model and the probability distribution of the shocks that are hitting the economy. And I think their problems arise. In other words, agents in these models are assumed to have quite incredible cognitive abilities. They are able to understand the complexities of the world. Not only that, but they can also figure out the probability distribution of all the shocks that can hit the economy. And that is quite extraordinary as a set of assumptions, especially in pandemic times, right? Who knew the distribution of the shocks, including a pandemic? That seems to me to be very far-fetched. And that also leaves the rest of the profession perplexed about what macroeconomists are doing. And that's why I think we need to develop different kinds of macroeconomic models. And that's what I'm going to do here. Models that do not make these assumptions about the cognitive capacities of individual agents. I will present a model that I don't claim to be the answer, just one possibility, but surely we have to search for alternatives to what has been done up to now. So, and the objective of this lecture then is the following. I will present a model in which agents have cognitive limitations, right? They do not understand the picture, the underlying model. They only understand and use small bits and pieces of information. And they will use simple rules to guide their behavior. And the way I will introduce rationality then is by a selection mechanism where agents that use these simple rules, these heuristics, evaluate how well these rules do, what their performance is, and after this evaluation are willing to switch to rules that do better. So it will be a switching model where agents look at the fitness, so to say, of the things they are doing, and then decide that when they could do better, they will switch to another rule. And this will always be an ex-post evaluation, right? Because that's the only thing we know. We don't know the future. We only know the present and the past, and we evaluate how well we have been doing up to now. So that will be the core of the model. So let me first present the basic behavioral model, and then I will apply to a number of problems. So here, I will first present the model structure, which is extremely simple. It's a new Keynesian structure, and I have an aggregate demand, an aggregate supply, and a Taylor rule. So the structure, basically three equations, and the aggregate demand and supply equation can be derived from optimizing behavior. I will not do that here. I will just show you the kind of reduced form that is obtained once you do this optimization. And here I show you the aggregate demand equation that explains the output gap, why T tilde is the output gap. And it's explained by a forward-looking component, the forecast of the future output gap, and a backward-looking component, the past output gap, right, with a weight A1. So in fact, in the simulations, some of the simulations I will show you, and I will tell you when that is, I actually switch off the backward-looking. Then I have a pure forward-looking model, right, where A1 is equal to 1, and then there's only the forward-looking component. So agents make a forecast of the future output gap, and that then determines the output gap today. And then the third term in that equation is the real interest rate. RT is the nominal interest rate, and ET pi t plus 1 is the expected inflation. So the difference between the two is then the real interest rate, right? And then epsilon t is going to be an error term, and I will assume throughout that this is an idea shock. So I don't want to introduce structure in the error terms because I want to show that much of the structure that is provided by this model is internally determined. I don't need to introduce structure in the error term to make the model fit, right? So that is basically the demand equation. And note that I have this hat over the ET, which means that I will assume non-rational expectations, the way I will define how exactly I want to do that. And so this will be the heuristics that I've been talking about in my introduction. So that is the aggregate demand equation. The aggregate supply equation is a kind of new Keynesian Phillips curve that explains the inflation rate. And again, you have a forward-looking and a backward-looking component. The forward-looking component is the ET pi t plus 1. Pi t is the rate of inflation. And the backward-looking is pi t minus 1. So this may arise, for example, because there are indexing schemes, and as a result, there is some inertia in the inflation rate, right? This is typically done in also in traditional mainstream models, but I can switch that off by setting B1 equal to 1, and then I have a pure forward-looking aggregate supply equation. And then the Phillips curve component is the output gap, right? You see that B2 times YT, which is the output gap. So when the output gap is positive, then you are in booming conditions, and this will tend to raise the rate of inflation. And eta t is then my idea residual. And finally, the Taylor rule describes the behavior of the central bank. And I assume here a central bank setting the interest rate RT, and the central bank has an inflation target pi star, and then will adjust the interest rate so as to steer inflation towards the target pi star. So if pi t exceeds pi star, then the interest rate is raised. But the central bank also cares about output stabilization. That is the C2YT term, right? Central bank typically, and I will stress later the importance of output stabilization in this model. And C2 measures the preferences of the central bank in terms of how much output stabilization it wishes to do. And finally, there is a lagged interest rate, because central bank typically find it costly to adjust interest rates too abruptly, and therefore will tend to smooth the interest rate adjustments. When C2 is equal to 0, we say that the central bank has strict inflation targeting, only cares about inflation. So that's the structure of the model, right? So very traditional. And now let me introduce the assumptions that I will use driving the expectations in the model. And let me first look at output forecasting, output expectations. So I will assume here that agents can use two rules to make forecasts, right? I've experimented in this model with more rules and a selection of rules, but I keep it simple. I want to go down to a situation where the model is as simple as possible. So I assume here two rules. One I will call a fundamentalist rule, and the other one an extrapolative rule. The fundamentalist rule is the following. Agents estimate the equilibrium output gap, and that is equal to 0. When the output gap is equal to 0, that is then the equilibrium value, and forecast the output gap to return to that equilibrium. So if the output gap is positive, then the fundamentalists think that the output gap will tend to return to 0. right? So we can call this a negative feedback rule. When something is too high, you expect it to go down. When it's too low, you expect it to go up, right? So that's the negative feedback rule. The extrapolative rule is just agents extrapolate the past output gap. Here again, we can have many different rules, but I will just take the simplest possible rule, just extrapolating one period, past period output gap. As I told you, I've experimented with more complicated, complex rules, but it doesn't really affect the dynamics of this model very much, right? The nice thing is to try to have the simplest possible model and to see how far we can get in terms of creating complexity, right? Because if you start introducing lots of complexity to begin with, no surprise that you will get something complex out of this. So that's what I want to do. How far can we get with such simple rules? So here are the rules, the fundamentalist rule. ETF is the expectation, the forecast made in period T by a fundamentalist. For the output gap is 0. It will go back to 0 again in one period. Again, I could have some inertia there, takes more time, and I did that, but let's keep it simple, right? Extrapolative rule is just extrapolating the past output gap. And so that's the extrapolative rule. So now these are the two rules that are available to these agents. And then the market forecasts are the weighted average of these two rules, fundamentalist and extrapolative forecast, and the alphas are the probabilities that agents choose one of these rules. So for example, alpha FT is the probability that agents choose the fundamentalist rule. And alpha ET is the probability that agents choose the extrapolative rule, right? And both obviously add up to 1. So that's the market forecast. And as you will see, there is a subscript T. In other words, these probabilities are time variant. They change all the time, right? And they can move, each of them can move between 0 and 1, right? And the sum must be 1, of course. I do something similar with inflation forecast. I'm not going to write everything down here. And I follow Brazier, where I assume that 2 inflation forecasting rule. 1 is that the agents believe the central bank. When the central bank says inflation target is 2%, they believe the central bank, and therefore they use that as their forecasting, right? And so they will always forecast the inflation rate to go back to 2% if it deviates today from the 2% target. So basically, that allows me also in the model to find out how credible the inflation target is by looking at the fraction of agents that use the target as their forecasting rule, right? And if everybody does that, then you can say, well, the central bank has a lot of credibility. So I have a natural measure of the credibility of the central bank here. The other rule is extrapolative again. So if you don't trust the central bank, you say, well, I'm just going to extrapolate the past inflation rate, right? And here also there will be a selection mechanism where agents choose the best performing rule, and they will be willing to switch between the two. So introducing discipline. One of the beauties of rational expectations is that it is in fact a disciplining device, right? You say expectations have to be model consistent. And that was, of course, intellectually very rewarding when that was introduced as a basic idea in our models. And of course, as I argued earlier, the drawback of that assumption is that you have to assume extraordinary cognitive abilities on human beings that I claim they don't have. And the evidence also seems to suggest that they don't have, right? So that's why we have to do different types of discipline than this one. However intellectually appealing this model consistency of rational expectations is. And so the way we do it then is through this fitness rule, right? So it's a selection mechanism based on the fitness of the rules that agents have. How do we do it? We use notions of discrete choice theory. This discrete choice theory also takes the view that agents are boundedly rational. And the way this is done in this model is to assume that the utility has a deterministic component and a random component. The way you can see that is as follows. The deterministic component of utility is something that as individuals we understand. We understand what our preferences are, but there's also a stochastic component, things that we don't understand about ourselves. And do some introspection, right? Quite often we find out we made some decisions based on stuff that when we look back at it, didn't seem to be rational. It was influenced by all kinds of things that what we call the stochastic, the random components. We were in a bad mood, we had headaches, and things like that that affects our preferences at the moment that we take a decision, and then can influence our decisions. So that's the way we do it here. And the first step then is to decide about the criterion of success. And how will we do that here? By looking at the forecast performance of a particular rule. So we have these two rules, and we check how well these two rules have done in the past in terms of forecast performance. And here I write it down, and we transform this forecast performance into utilities. So look at UFT. So on the right-hand side, you have the forecast errors that were made using the fundamentalist rule, right? So you see YT minus K minus 1 minus the forecast made in one period earlier for the output gap, right? And we square that and we give a weight, omega K, with these declining weights. And with the minus signs, this UFT is then the utility that an individual gets from using the fundamentalist rule, right? So the higher the U, the higher is that utility. In other words, the lower has been the forecast error using that fundamentalist rule in the past. And the UET is then to be interpreted similarly, is the utility of using an extrapolative rule based on past performance. So that will be the criterion of success, and the decision rule will then be based using, again, discrete choice theory by comparing these performances, taking into account the stochastic nature of the preferences of these agents, and that then, just going to give you the result, gives you the outcome, right? These probabilities, the probability of agents using the fundamentalist rule, alpha FT, is given by that expression, the exponent of gamma, which I will explain immediately, times the utility of using that rule divided by some averaging procedure of both the fundamentalist and the extrapolative utility of using these rules. And as you can see, when the utility of using the fundamentalist rule increases relative to the utility of using an extrapolative rule, then the probability that agents will use that rule increases. In the limit, it can go to 1, right? That everybody uses a fundamentalist rule, or vice versa, the extrapolative rule. What's the function of the gamma? This is sometimes called the intensity of choice parameter. It gives a parametric value to the extent to which the deterministic component in utility determines the actual choice. If gamma is equal to 0, that's a situation where everything is stochastic. You just don't understand yourself. You are bewildered about your own preference, right? Then gamma is equal to 0, and when you work it out, then you see that these alphas are equal to 0.5. You toss a coin. You just don't know, right? You toss a coin. It's too much noise there. And as gamma increases, the deterministic component becomes more important. In the limit, gamma can go to infinity, and then you will always have one of the two, right? The one that works better will always be be chosen, and that will be one. So then you come close to what we could call a rational decision, right? So that is the way these rules are selected, right? Okay, so that's to repeat. Agents use two potential rules, fundamentalist and extrapolative. They check how well these rules have been doing in the past in terms of forecasting performance, and then they select, or they select the one that is most likely to have a better outcome. And so that's the way we do it here. Now, we can also extract from this analysis here something that I will call animal spirits that plays an important role in the model. It's an index of market sentiments that we call animal spirits, and which reflects the degree of optimism or pessimism implicit in these forecasts, right? And here's a definition. It's an index, ST, that can go between -1 and +1. -1 is extreme pessimism, +1 is extreme optimism. And ST then takes the following value. Look at the expression there. If the output gap in T-1 is positive, right? Then what do you have? Well, the extrapolators then continue to extrapolate a positive output gap. So I call these people optimists, right? They have an optimistic forecast. What do the fundamentalists do when YT-1 is positive? Their forecast is going to decline, right? So they are the pessimists. So the alphas here can also be interpreted as fractions, right? So the alpha ET is the fraction of optimists, and the alpha FT is a fraction of pessimists when YT-1 exceeds 0. And then you can see that if the fraction of optimists, alpha epsilon T, is higher than alpha FT, then this is positive, and you can say market sentiments are positive. In the limit, this can go to 1, where everybody is optimistic. Everybody thinks the boom will go on in the future. And when YT-1 is negative, then it's the reverse, right? Then you can see that actually the fundamentalists are the optimists, because they think that it's going to go up again, right? So they are optimists, while the extrapolators are the pessimists, because they think it's going to go on, the recession is to go on. And I extract the same kind of information about optimism and pessimism that can move between -1 and +1. So this is actually something that can be extracted in a linear way from these fractions that I have derived in the model. But I will show quite often these indices of animal spirits, because the intuition of the model comes out better if I do that. I calibrate the model. This is a highly nonlinear model, so I calibrate it using the parameters that I found in the literature, and I simulate it. So this will be using simulation procedures when IID shocks with standard deviations of 0.5, which means that the time is typically like something close to a quarter, right? But that's the kind of standard deviation of the shocks you find over a quarter. I also do lots of sensitivity analysis, but I will show you some of them here. So that's what I do here. Let me now show you, to start with, a prototype simulation of that model, given the assumed parameters and the IID shocks, right? So you see the output gap. The output gap there moves up and down, right? And then you see below the animal spirits that move between -1 and +1. And you observe immediately a very strong correlation between animal spirits and output gap, right? When you calculate the correlation coefficient, it's something like 0.9 or 0.95. So typically, animal spirits tend to drive the business cycle. So movements of optimism and pessimism drive the business cycle, but there are also moments where there's very little going on in terms of market sentiments, when animal spirits fluctuate around zero, right? And not much is going on. Look on the right-hand side, there I show you the histogram of the output gap. And so you can see here that it's not normally, well, you don't see it, I guess you see it, it's not normally distributed. I did some testing, right? And I reject normality of the distribution of the output gap. And you can see that it has some fat tails there, right? And too much concentration around the mean. And this is related to the histogram of the animal spirits that I show you below, where you find high concentration of market sentiments around zero, where there is no particular market sentiment, right? Optimists and pessimists offset each other more or less. But then once in a while, you have bursts of either optimism or pessimism. You have extreme values of optimism +1, of pessimism -1, and that coincides with fat tails in the output gap distribution and to the wild movements in the output gap. So this is a model that actually predicts that much of the time the business cycle will be relatively smooth. Not much is going on. It's a little bit like a situation we had before the financial crisis, right? When macroeconomists were very optimistic about how they have achieved wisdom in macroeconomics, and this was even called the period of great moderation, right? We had like in the time of physics, just before Einstein, physicists also thought they had now reached the pinnacle of knowledge, and macroeconomists also tended to believe that they had achieved that, and now we had actually business cycles wouldn't occur anymore. We can master all this. This was great moderation. And indeed, and the model tells you here that there are periods of great moderation, right? That can last for quite some time. But once in a while, suddenly you get a boom-bust pattern, right? And how does it come about? Well, it can come about just by accident, by a series of random shocks that at some point, for example, make those who are optimistic performing better in their forecasts, right? And they are doing better. And then through this mechanism that I explained, attracting others into using an optimistic forecast. And you get some kind of herding effect whereby more and more people become optimistic up to a point that everybody has become optimistic, and you are pushed into a boom. And at some point, this will unravel and we get a crash, right? And so this is a model that actually produces booms and busts once in a while, great moderation much of the time, unpredictably creating booms and busts situation, right? And note also what drives all this is a correlation of beliefs, right? These are all individual agents, but at some point, these beliefs of optimism get correlated by the very fact that you are doing better when you are an optimist at some moments. And this leads then more people to become optimists and creating waves of optimism. As I said, the timing is unpredictable, and optimism and pessimism are self-fulfilling, because when you're optimist, well, you invest, you consume, and then output increases and you are validated. You were right to be optimistic, and this attracts even more optimists. So that's the story that this model tells you, right? So it's a model that actually predicts that business cycles are endogenous. So it's an endogenous theory of the business cycle, right? It also tells, it's made possible by the dynamics of animal spirits, and the empirical evidence suggests that the distribution of output gaps is non-Gaussian. There's a lot of empirical evidence that indeed tells you that it's not normally distributed, right? There's excess kurtosis and fat tail. So that's indirect empirical evidence that this is indeed what should happen. Now, note in traditional DSG models, you can also do it, if you like, by giving all the action to the error terms, right? You have external shocks, and if you make them serially correlated, then you will also produce all this stuff. And if you have large enough shocks, you will also produce large business cycle movements. But this I call an exogenous business cycle theory. It's not generated internally. I call it a meteor theory of the business cycle. Once in a while, a meteor hits you and you get a very strong stuff in your economy. But that's not very satisfactory. I think we really need theories that are capable of generating this pattern that we find in capitalism, right? It has been going on for centuries, that much of the time there are ripples, and then once in a while you have booms and busts and all that. So that's the, by that, I don't want to say that large shocks cannot occur, right? I mean, and that like the pandemic today was certainly a large shock. So I'm not arguing that sometimes large shock cannot occur, but a theory that relies on large shock to explain why sometimes we have large movements is not a very satisfactory theory. We have to do better, right? Because otherwise we always, as a macroeconomist, we always have to ask other scientists, why do we have these large movements in output? Oh yeah, because there was a virus. Today, this, of course, that is the way to do. But sometimes you don't have to ask other scientists, and you can generate it yourself. And that's what I do in this model. Okay, let me say a few things about monetary policy and the role of output stabilization in this model. I will do that in a very simple way by constructing trade-offs. And then when I've done that, I will discuss the transmission of shocks, right? And I will make a distinction between large and small shocks because, as you will see, it matters in this model, right? So, but first, monetary policy and the role of output stabilization. The way I do it is by constructing trade-offs. So I simulate the model 10,000 times. And each time I compute average output and inflation variability for different values of the Taylor rule parameters. Remember, the Taylor rule parameters give us an indication of how much the central bank cares about inflation or output stabilization, right? But the way I will do it is to check the output stabilization effort of the central bank. So I will allow the coefficient C2, which measures the desire of stabilization of output, to change from 0 to 1, right? And so then I compute the variability for each of these values of C2, and then I obtain something like this. I also change the values of C1, but let me postpone the explanation. So I have lines here for different values of C1, which is the coefficient that guides the inflation preference of the central bank. But here I do the following. Look at the chart on the left-hand side. On the horizontal axis, I set out Taylor output parameter. Oh, I see that, in fact, I varied it over longer range than 0 to 1. It's from 0 to 3, right? So I allow the output parameter in the Taylor rule to vary between 0 and 3. And then I compute for all these values the standard deviation of the output gap. And these are these downward sloping lines. And you get the result that you expect when the central bank makes more effort to stabilize output. Then the standard deviation of output will tend to decline. Output gap, when I say output, I always mean output gap, right? So that's the normal downward sloping line. Now look at the right-hand side, because there you find different results than in mainstream models. Here again, I have on the horizontal axis the Taylor output parameter, right? And then I simulate the model each time 10,000 times, and I compute the standard deviation of inflation, which I put on the vertical axis. In the standard model, you have just upward sloping lines. If the central bank attaches more effort and importance to output stabilization, you always pay a price in the sense that inflation will become more variable, right? That's the price that you always pay for output stabilization. But not here. Here you find that when you start at zero, no output stabilization, and you gradually increase output stabilization, actually inflation volatility also declines, like output volatility does, right? Up to a certain point. When you go too far in output stabilization, then the inflation volatility tends to increase. You start to pay a price. But there is a range here where I get results that are different. I will come back to interpret that in a minute. And then I bring the two together, right? I bring the two information together. Now I set the standard inflation on the vertical axis and the standard deviation of output gap on the horizontal axis. And I bring these two graphs together and I get my trade-offs. So let me go to the trade-offs. I will say a little more about the different trade-offs here, but let me start with the blue line. And I start at point A. So this is the point where the central bank doesn't do any output stabilization, right? And then you get a particular configuration of volatility of output and inflation. And then the central bank starts increasing its effort to stabilize output by increasing C2. And then we move down along this blue line, right? In other words, you can call it a win-win situation. Business people like this thing, huh? Like this is a win-win situation. The central bank, by stabilizing output, actually reduces both the volatility of output, no surprise, but also the volatility of inflation. Up to a point, when you go to the minimum point of this blue line, then you get the normal downward sloping trade-off. If the central bank goes further, then it pays a price. Then it starts being confronted with the trade-off in that by doing more output stabilization, it will pay a price in terms of more inflation volatility, right? But so we have a non-linear relationship here. And where does that come from? Well, it comes from the fact that if the central bank doesn't do any output stabilization, then we get these boom-bust scenarios very often and very intensely. And the system is very unstable, right? And as a result, by doing some output stabilization, the central bank not only stabilized output, but also inflation. Because as you remember in the supply equation, you have output gap. And if the output gap is very unstable, then inflation will also be very unstable. So by doing some output stabilization, the central bank takes out the fat tails, the extreme values of animal spirits, reduces the probability that this occurs, and as a result stabilizes the whole economy, both output and inflation. But it shouldn't go too far. If it goes too far, then its credibility in stabilizing inflation might be undermined, and that's then the negatively sloped line that we get there, right? Now, let me say one thing about the importance of C1. C1 is the intensity with which the central bank applies inflation targeting, right? When C1 is high, it really gives a lot of importance to inflation remaining close to the target. And then you can see that C1 increases, these trade-offs move downwards. So you tend to improve the trade-offs, right? But there is at a certain point, you stop moving down, right? There is a point where trying to do more has very limited additional returns. So inflation targeting is also important. So this is not a model that says that you can actually not do inflation targeting. No, inflation targeting remains important, but so is output stabilization. So interpretation, I think I said all this. let me go a little quicker. So let me just about the philosophy of this model, right, compared to traditional model. This model recognizes that that the role of the central bank in stabilizing economies is very important, right? The central bank is also there to stabilize an otherwise unstable system. Unstable in the sense here that it creates so much volatility that it can actually disturb societies, right? By excessive optimism and pessimism, and can lead to so much volatility that societies are disrupted, and central banks cannot afford this, to allow this. So it has a fundamental responsibility in stabilizing a system that otherwise is not sufficiently stable. While the contrast with traditional mainstream macro models of these days is a belief that in the end the markets will do it for you. Of course, you can help them. Huh? The DSGE models are new Keynesian. They recognize that there are some rigidities, and therefore that the central bank can help. So the modern DSGE models do not say that central bank should not do any stabilization, no. But the model, it's a framework of equilibrium model. Strong inflation target improves the trade-offs. Right? That remains key. So this is not something that tells you, oh, you can do whatever you like with inflation. No, it's important to keep that in mind. Okay, last point I want to make, last element is about transmission of small and large shocks. In mainstream models, it doesn't really matter whether you have large or small shocks, right? These are typically linearized models around the equilibrium, and typically you will take small shocks because you shouldn't really take large shocks if you have linearized the model around the equilibrium. But the professor has been very cavalier about this difference between small and large shocks. Here we'll see that it matters, right? So I will compute impulse responses to large and small demand and supply shocks. And large, I will mean 10 standard deviations, and small, 1 standard deviation, right? You could say 10, is that not, well, I say the COVID shock was something like 10 standard deviations, right? When you look at what happened the first half of last year, this was like a 10 standard deviation shock. We also had the financial crisis of 2008, 2009, and the recession at that moment was also a very large shock, maybe not exactly 10, but something between 5 and 10. So it occurs regularly, right? So we better look at the implications. So let me show you the effect of a large supply shock here and impulse responses. Note that I define my impulse responses in terms of multipliers. So I divide the impulse response, the effect on output gap or on inflation, by the shock, right? The size of the shock. And so here, what on the left, upper left, you see the impulse responses of output gap. And this is supply shock. So output tends to decline. Inflation tends to go up. But note, and this is a very large shock, right? What you see here is a clustering of the trajectories around 2 paths. One that looks bad, the one that goes down very deeply. And then there is another one that goes down a little bit, but recovers very quickly, right? So it seems that with these large shocks, you have 2 trajectories. One that quickly goes back to equilibrium, and another one that takes a long time to go back to equilibrium and is very deep. Note also there's great uncertainty about this, that all these lines are just one impulse response, right? And I have 1,000 impulse responses here. So you can see that there is a problem of predictability here about these impulse responses. And then I also show you the inflation impulse responses. Again, 2 trajectories, one that goes quickly back to low inflation, another one that takes a long time. And then also in interest rate, that will turn out to be quite important. You can see the interest rate after the shock bifurcates. There seems to be a path where the central bank increases the interest rate even further, and another one where it quickly reduces the interest rate. I will come back to that to see where it comes from, and I will show you that it has something to do with initial conditions. So this is a model that also stresses the importance of initial conditions. What were the initial conditions where the shock was introduced? And that determines a great deal about the trajectory afterwards. So this is the large shock. Small shock, one standard deviation. Very different pattern. Again, here there is no structure. I don't see much structure here, right? And you can see, well, of course, output tends to decline, but then it goes back, and inflation tends to increase, but then goes up and can go down. So it's very unpredictable. So you see, with low standard deviation, surprisingly, it's much less predictable which path the economy will take after the shock, right? So again, these are multipliers. Huh? So of course, when you have a small shock, output will decline by less than if you have a large shock. Huh? But so I've normalized it by using multipliers. Another way to look at this is the following. It's like I take an intersection after 12 periods, right, of all these impulse responses, and I show you the distribution, right? With the large supply shock, you can see that it's bimodal. So this is the effect on output gap after the large supply shock after 12 periods. And you can see that there seems to be convergence around two paths, they are not equilibrium really, but there are two paths that are being taken. One is a bad one with a very strong negative effect. Another one is a good one where output gap is close to zero, just mildly negative. And something similar with inflation and the interest rate also. You see two clustering around an interest rate that actually clusters around zero, and another one where the interest rate is actually positive, right? And when the shock is small, then we have a diffuse pattern. There's very little predictability here about what exactly the path will be, okay? So how can we interpret this, right? We have two trajectories. Let me first concentrate, this is supply shock. I will say something about demand shock later, huh? So we have a good trajectory, which is a mild decline in the output gap and a relatively quick return to the steady state value, and a bad trajectory, a very deep decline in output and a long and slow recovery. And these trajectories seem to be related to the interest rate trajectory observed after the shock, with a bifurcation. There is one trajectory where the interest rate tends to decline quickly, another one where the interest rate tends to increase, right? And so I will explain that later, what exactly and why exactly we have this. So, but it seems to be related to that. In the good trajectory, it looks like, let me go back to here. In the good trajectory, the output gap tends to be restored very quickly. The negative effect is being restored very quickly, and the interest rate also is going down. In the bad trajectory, the interest rate is raised and the output gap goes down even further and has a very long trajectory back to equilibrium. So there is something here, the reaction of the central banks, that is different depending, and as I will show, depending on the initial conditions. Right? The initial conditions actually will drive on that response and therefore also drive the trajectory later. And with the small shocks, we don't find this. There's very little predictability, very little structure in the distribution. And here the fundamental reason is that the signal to noise ratio is very small. And this is one standard deviation. When you have a shock of one standard deviation, when the initial conditions are also full of noise with the same kind of standard deviation of the noise, then the signal to noise ratio will be very small, and as a result, it will be very difficult to predict what the shock will do to you, right? It's overwhelmed by the noise, and so this is something here. So it's not unimportant because, as you are aware, we often see in papers on macroeconomics these impulse responses, and actually there is no relation to initial conditions in these models because they don't matter. But in fact, those initial conditions are so important. You ask to a practitioner whether initial conditions matter, and we always tell you, yes, of course, the initial conditions matter, right? But I will come back to that later. Demand shocks, very quickly, something similar there. With demand shocks, I have a large shock and small shock. When you have a large shock, so this is a negative demand shock, right? Output gap declines, but also you can see a pattern of two trajectories, a good one and a bad one. For inflation, oops, it's less pronounced, but impulse responses of the interest rate, something similar. With the small shocks, much more diffuse and unpredictability. Here I show you the frequency distribution of the impulse responses. Here I take 4 periods after the shock. Note the following, an important difference between demand and supply shocks is that when you have a supply shock, the central bank is typically forced into a dilemma situation, and as a result, will not be able to do a stabilization very well. And that this model explains why the adjustment is much more protracted. While with demand shocks, the central bank doesn't face this dilemma because output and inflation go in the same direction, and therefore it can use its monetary policy instrument in a very clear way and stabilize the economy much better after demand shock than after a supply shock. And that also explains why the return to equilibrium with a demand shock is typically shorter. So I take here 4 periods, and you see the same feature bimodal. With a large shock, you have a good and a bad trajectory, and it's also related somehow to the interest rate. Small shock, we have a very much more diffuse pattern. So we have similarities with supply shocks in the trajectories. The difference, as I told you, has to do with the fact that the return to the steady state appears to be much quicker after the demand shock than after the supply shock. And that, as I told you, with the supply shock, the central bank is put into a dilemma situation, cannot stabilize very well. With a demand shock, it doesn't face this problem. The power of the predictive power of initial conditions, this will be the last point that I want to make. How well do initial conditions predict? And so the way I will want to do that is as follows. I will again take large and small shocks, first supply and then demand. And now I will do the following. I look at the initial conditions of inflationary expectations. These are put on a horizontal axis here. So this are the inflation expectations to the extent that they deviate from 0. And so I've normalized the target, inflation target, around 0, right? So if you have a positive number here, inflation expectations, that's a situation where initially, before the shock occurs, agents expected high inflation. So in other words, this must have been a situation where prior to that, this was an inflationary environment and agents expected a lot of inflation. When you're on the left-hand side of 0 minus, so that is a situation where agents initially, before the shock occurs, expected very low inflation, less than a target, right? So you can say, for example, in the 1970s, we had a supply shock, right? And then inflation expectations was very high. So initial conditions or inflation expectations were positive on the right-hand side of 0. Now with the pandemic, the inflation expectations were very favorable, very low inflation expectations. We're on the left-hand side. And now I ask the question, do these inflationary expectations predict the trajectory of the impulse responses that you will have after the shock? And indeed, it does very strongly. If you have inflation, positive inflation expectations, right, then you can see all the points here, all these dots. These are, again, what I showed you, the distribution, right, after 12 periods, the output gap after 12 periods. All the dots are on the clustering around -1, -1.2. the bad trajectory. So these are all the points of the bad trajectory after 12 periods. So if you have strong inflation, expectations of strong inflation prior to the supply shock, then this model says your trajectory after the supply shock will be a bad one, with a very strong decline in output gap and a very protracted movement towards equilibrium, like in the 70s. If, on the other hand, before the shock, you had very favorable inflation expectations, inflation expectations were below the target, then this model predicts that you will get into the good trajectory with, of course, some decline in output, but a quick recovery from the negative output gap, right? So this could be said to be the pandemic effect, right, today. Note that other initial conditions, our initial expected output doesn't have much predictive power, right? It's all clustered there. And I did also some econometrics. I will not show it because of time constraints, but we look at, I set up an econometric model, a bimodal econometric model, to find out whether these initial conditions, not only these, but also other initial conditions in the model have predictive power, and the strong predictive power here of inflationary expectations comes out. With small supply shocks, you have very little predictive power of the initial conditions, almost none, right? Just a little bit. You can see a little bit, but not very much. And this has to do with what I told you earlier about the signal to noise ratio that is very small. What's the underlying mechanism? Right? What is the story behind this, right? Well, as I told you before, when I showed you the initial figure, you have a bifurcation of the interest rate, right? And there is one part that quickly goes up. Maybe I show you that quickly here. Yeah, here. Okay. So look at down there, the impulse response, right? After the shock, at the moment of the shock, the interest rate is raised, and then there is bifurcation. In one case, the interest rate goes down. The other case, the interest rate goes up. The interest rate that goes down is in fact the path that coincides with the favorable trajectory. And that is the one that is predicted by low inflation expectations. So if you have low inflations to start with, what's happening then? Well, at that moment, the negative supply shock that tends to reduce output, but also raise inflation, has relatively little impact on inflation because agents didn't expect much inflation. In fact, they expected inflation to be very low, right? And as a result, inflation actually does not increase very much. And as a result, the central bank will be very much induced to look at the output gap that has gone down, and it lowers the interest rate, right? Conversely, if you start from a high inflationary environment with high inflation expectations, the output gap, the negative supply shock then raises the inflation very much so, forcing the central bank not to lower the interest rate, but to raise the interest rate. And as a result, making the output gap decline even worse and pushing the economy into the bad trajectory. So that's essentially what is going on here. So it's initial conditions that actually at a certain moment force the central bank to go in one direction or in the other one, and then pushing the economy either in a favorable or a good trajectory or a bad trajectory. And the bad trajectory is then one where the decline is very protracted and takes a lot of time to go back to equilibrium, right? We had very long time to get out of this mess, right? And it all depends here on initial conditions. When did the shock occur, right? Okay, I think I said all this. When inflation expectations are initially favorable, below the inflation target, and the upward movement of the inflation immediately after the shock is quickly corrected. And as a result, the central bank, observing a relatively favorable inflation outcome, reacts by reducing the interest rate to deal with the negative effect of the supply shock on output. And this mitigates and forces you to a favorable and good equilibrium, right? Let me quickly go to the demand shocks, but I will be a little faster here. There we find the demand shock. I've shown you there's also bifurcation. Here it's the initial expected output that matters a great deal. So here I show you the initial expected output. So if it's positive, it means that there was a lot of optimism. Animal spirits were very optimistic at the moment the negative demand shock occurred, right? And when it's negative, there's pessimism because there's a recession, for example. And then when you have a negative demand shock, if there was optimism before, then you get into a positive trajectory, a mild trajectory. If there was a lot of pessimism before, the negative shock reinforces this, and you are pushed into this much more unfavorable trajectory with much longer period to get out of this, right? Okay, let me go to the conclusion. So this is an alternative model, right? And again, as I told you earlier, I don't claim that this is now a revolution or something, but it's another way of thinking about the macroeconomy. It's a little bit an attempt to think out of the box, right? And there have been many more attempts to do so. And there are other approaches like agent-based models that are much more detailed. My model is much less detailed, right? But I think it strikes to the heart of endogenous business. We can write says that it can, but we have to do better. I have done a lot of extensions of the model, and this can be done. I've added fiscal policies and interaction with monetary policy. The multi-country model, that multi-country model also has an interesting feature, that is that this contagion of animal spirits when you have different models that can actually act quicker than trade, right? There's contagion there that can arise, and that links economies quite quickly because there is contagion in animal spirits, in optimism and pessimism. And I also extended this model, allowing for zero lower bound and showing that if your inflation target is too close to the zero lower bound, you may push the economy too often into negative territory and create chronic pessimism that leads to a situation when you stay there very long time into low growth and high unemployment. So many more extensions are possible, and I think it's an exciting way of thinking about the economy, and that's how I want to conclude. Thank you for your attention.
Thank you very much, Paul. I was about to say this is a very exciting new path of research, and I'm sure that it will develop in the years to come. As you said, there are different attempts to do these things with agent-based models, and I've been involved in that very much. But I think these stylized models of yours are very fruitful and help to think about what can happen. So endogenous business cycles, tipping points, all these things are very close to my heart. And while listening to you, I was thinking of Anatole France's quote, who said, "It is human nature to think rationally and act absurdly," which I think ties well with these behavioral assumptions on choice theory and intensity of choice and so on. So it's also very good because Cars Holmes gave a talk before you, and he investigated a lot these heuristic forward-looking and backward-looking rules. And I think it ties up very well with what he said. And I think there's more and more empirical evidence, even from the lab, that people are actually using these rules. Just a question, a technical question. You call extrapolative something that I'm not sure I would call extrapolative in the sense that it's really completely backward looking. I would call extrapolative something like the expected value of yt plus 1 minus yt is a proportion of yt minus 1. So the extrapolative for me is a kind of trend thing that doesn't seem to be the case in your model. Have you tried to look at these, what I would call truly extrapolative rules? I think they would be much more destabilizing, but maybe interesting as well.
Yeah. That's a good question. Of course, I normalize everything around 0, right? So therefore, I have no trend, right? So of course, you could say that the 0 is the trend, right? So
no, but it would be a local trend.
Yeah, sure, but that's something to look at. I haven't done that. It may introduce richer dynamics into the model. Yeah, that's a good point. Yeah.
The other thing I wanted to ask you, which I wasn't completely sure of, is that the utility function of your agents is now related to the prediction error they make in the past. But in what way is it really utility? I mean, can you relate these errors, prediction errors, to something real, like their consumptions, or why are they caring about predicting the future? Can you have a story that relates the the accuracy of their prediction to something that's more related to real utility? I mean, to gain or to reward.
Yeah. Well, I think the story you can make, for example, inflation prediction, right? If you have to make come to a wage contract and you have to forecast inflation, then if you make good forecasts, this will be good for employers and employees. And if you make bad forecasts, then there will be a loss for you, right? For example, if you forecast inflation to be too high, then the employers will lose, because they will agree into a wage contract that allows wages to increase too much while inflation actually was low. That then turns out to be lower, and therefore there will be losses for them, right? So in that sense, there is a connection with welfare, right? Making good forecasts is welfare improving, given that this will affect the future path of your wages, and for the employee, this is his earning power. For the employers, this is his profits in the future, right? Of course, I do not model this explicitly, right? That you could say is the weakness. It's a kind of it's a kind of reduced form.
Yeah, that's fine. But so you have more in mind in this forecast the firms or the households, or both?
Of both, yeah, that's right. And for output gap, it's something similar, right? You make firms that invest, they base their investment on some forecast of future demand. If they make a mistake there, they might either not have invested enough, or have overinvested. Again, I don't model that problem explicitly, but that's a story that links performance of forecasting with welfare.
No, that's fine. Okay. And so last comment is that, so we've used highly simplified agent-based models to have a go at all these questions that you raised in your talk. And so recently we adapted this agent-based model to the COVID crisis. And what's, I think, very interesting is that we find very similar conclusions to you, in the sense that we also have this existence of two types of trajectories depending on the amplitude of the shock. One where recovery is V-shaped, and the other one where actually I mean, in your case, there's slower recovery. In our case, you fall into a second equilibrium where output is permanently reduced. But what I think is interesting is like a little bit in climate science, that if different people have different approaches, the fact that it leads to similar scenarios is quite interesting, because it promotes the idea that maybe some conclusions are more general than the models, than the particular modeling assumptions that people make. And I think that it makes these predictions more credible in a way.
Yeah, that's interesting. Yeah. Okay, very good.
So do you have in your model actually the possibility of multiple equilibria?
Not strictly speaking. The model sometimes under particular configurations of parameters can produce chaotic behavior. So chaos in the mathematical sense, right? But that is not really multiple equilibria, right? And this model doesn't really have multiple equilibria, but this being said, for all practical purposes, like I showed this trajectory, it's as if there are multiple equilibria, because this is quite a long period of time. So we impose that in the very long run, ultimately, we will go back to the steady state. But in between can be such a long period that it is as if it's multiple equilibria.
Sure. Well, Paul, thank you very much. I'm sure that this will be very useful for the audience, and I really hope we can continue this conversation when the situation is closer to normal. Okay. Thank you very much, and goodbye.
Thank you very much, Jean-Philippe. I appreciated it very much to be able to do this, and I also hope that we will be able to continue this. Okay.